Okay, video on D1, trig functions. Okay, so these are the 4 expectations in the learning goal. So you have to determine the exact values using special triangles of sine, cosine, and tangent. We need to determine values of trig ratios from 0 to 360. And we have to prove trig identities and use the primary trig ratios and the sine and cosine law. And both of these things are from grade 10 math. And they're just carried forward this year with the expectation that now you could maybe solve some problems using those. Okay, so let's go through all this stuff. So I'm going to start with the review of grade 10 trig. Just basic grade 10 stuff. If we have a right angle triangle, that means one angle has 90 degrees, then we can use our primary trig ratios, which are sine theta equals opposite over hypotenuse, cos theta equals adjacent over hypotenuse, and tan theta equals opposite over adjacent. So we can use these ratios to solve for missing side lengths or angles. And we could also use the Pythagorean theorem, a squared plus b squared equals c squared, if we wanted to. So that's our primary trig. And sometimes you may have heard that called SOHCAHTOA, which just kind of helps us remember that sine is opposite over hypotenuse, and etc. Okay, and then there's also the sine and cosine law. So those things are used when we have triangles that don't have a 90-degree triangle in them. So the sine law is set up like this: a over sine A, b over sine B, and c over sine C, although you would only use 2 of those ratios at once. And they're labeled so that this top guy A here is the side length, and it's right across from angle A. And if this was side B, it would be angle B, and if this was side C, this would be angle C. So that's how that's set up. So basically, in order to use the sine law, you have to ensure that one ratio is fully completed. You have the side length and the angle. So in order to use the sine law, you must know, it doesn't matter which one, but you must know an angle and a side length that are across from each other. If you don't know that, then you're not able to use the sine law. So you at least must have one full ratio, and then you just solve for an unknown. So for example, if I had 12 meters and 30 degrees, and maybe I knew that this side was 14 meters, I could use it to solve for angle B by just subbing stuff in. So I'd have 12 over sine 30 equals 14 over sine B. And you can set these ratios if you want to. Like if you don't like having that sine B on the bottom, you can simply flip your fractions and make it sine 30 over 12 equals sine B over 14. If you like that better, you can flip them as long as you flip both sides. Okay, so if I flipped mine, now I just want to isolate sine B, so I'm going to multiply both sides by 14. So it'll cancel that out. I'm going to multiply that by 14. So punching that on a calculator would give me, I have no idea because I don't have a calculator. Time out. Okay, got a calculator, so that would give me 14 times sine 30 divided by 12 is 0.58333 repeating. That would be equal to sine B. And then in order to solve for the angle, I always have to take the inverse sine. So the sine -1 of that giant number. And I would find out that sine B is, angle B is 36 degrees if I round to the nearest degree. So now I know that's 36. Can also use angle properties, like I know all of the angles in a triangle add to 180, so it would be really easy to find the angle right there. And then I can just do the sine law again to find this missing side. Okay, so that's sine law. Cosine law is a bit more complicated, but basically if I can't use the sine law, I'm going to have to use the cosine law. Really just two instances where you need the cosine law. One where you would know, for example, two side lengths, like this, and perhaps the angle that's in between those side lengths. So in this case, you would have to use the cosine law. Couldn't use the sine law. And if you have a case like this, you in fact can only solve for a side right off the bat. So here's our cosine law formula from last year. And as you can see, in order to solve for side A, I need angle A and I need side B and side C. So I need to know B and C and also angle A, which I have. So you can use that to solve for this missing side just by plugging into the formula. The other way the cosine law is rearranged is by isolating cos A, which turns the formula into b squared plus c squared minus a squared divided by 2bc. And in order to use that version of the formula, where you're trying to solve for a missing angle, as you can see from the formula, you'll need to know the lengths of all sides of your triangle. So for this case of the cosine law, you would actually need to know the length. I'm just making this up, so this is probably not going to exist. You would actually need to know all three, and then you could solve for a missing angle. So I'm not going to go through those ones. They're a review from grade 10, so if you need any more help with them, let me know. But yeah, so that's your grade 10 trig, so that's that stuff. Okay, let's work on our special triangles, because that's pretty important. It's pretty important for next year, too. Okay, so we learned two special triangles, and they look like this, that you should remember for the test. There's two of them, and you're going to use them again in grade 12. So we have a 30, 60, 90 triangle, and the side lengths are root 3, 1, and 2, and we proved this in class. And you also have a 45, 45, 90 triangle, side length 1, 1, and root 2. So these special triangles are they're pretty cool because they can help us get exact values. So for example, if I wanted to know what the sine of 60 degrees is, okay, so let's just say I punched into my calculator. I'm going to do that once I get my calculator here. Okay, so let's say I punched in sine 60. My calculator tells me that sine 60 is equal to 0.866. Great. But if I use my special triangles to determine what sine 60 is, I can get an exact value because 0.866 actually keeps going. It's like 0, 2, 5, 4, etc. It's just going to keep going forever. But if I use this special triangle, I can get angle 60, and then I know sine is opposite over hypotenuse. So I can use this to get me the exact value, which is root 3 over 2, which root 3 divided by 2 is actually equal to that. But now I have like a very exact value. No rounding, no decimals. It's exact. So these special triangles can help exact values, which we sometimes might want. Okay. So it's helpful because we can find exact values sine, cos, and tan of 30 degrees, 60 degrees, and 45. So that's pretty cool. But it's even cooler because we can extend that to actually go all the way to 360 degrees. So if you recall the sine curve or the cosine or whatever, let's start with sine. The sine curve looks like this. And it keeps going in both directions. But some highlights. So here we go. It passes through 0. So on the x-axis, it's in degrees. The y-axis has a max of 1 and a min of -1. Up here at the top is 90 degrees. Across the x-axis is 180. Right here is 270 degrees. And right here is 360. I find this helpful to remember because I can look at the sine curve, so this is sine, and I can immediately tell values because like I have this curve memorized, so I know if I wanted to find the sine of 0 degrees, oh, I know that's 0. If I find the sine of 90 degrees, I know 1. and sine 180 would be 0, and sine 270 would be -1, and sine 360 would be 0 again. So I feel like it's very helpful for like just finding those specific values. And also, if you didn't notice, the sine curve is split up into the quadrants. So if I split it up into like 90, 180, 360, this is quadrant 1, this is quadrant 2, this is quadrant 3, and this is quadrant 4. So when I look on a graph, these quadrants, and if you recall in class, we did something with putting angles on a graph. This guy, our initial arm, and that starts at 0 degrees. And then when we rotate our initial arm around, we reach 90 degrees, 180 degrees, 270 degrees, and then back to 360. So a complete circle. So I could graph an angle, like for example, if I went to quadrant 1, I called this guy my terminal arm, and I could create a triangle with this terminal arm. Let's say I created one of my special triangles, like the 45 one. So I made this angle 45, this one's 45. This would be 1, 1, and root 2. So this is quadrant 1. So in quadrant 1, I can see that all values are positive. So all of these values are above the x-axis. They're all going to have positive values somewhere between 0 and 1. So when we're at 45, which would be like halfway, the sine of 45 degrees is going to be 1 over root 2. So that's pretty cool. Everything's positive. It's easy peasy. Okay, well actually I can keep going with this thing. Sorry, I'm just going to erase what I have. So I can extend my terminal arm to go into quadrant 2. There you go. There's my terminal arm. So now I've created this angle called the principal angle. But he has a related angle. So if I connect my terminal arm with the x-axis, I can create what's called, right here is called a related angle. So that's a related angle. And let me get my principal angle and everything by using SOHCAHTOA, so I don't have to like use something other crazy thing. So let's say I use my 45-degree triangle again, and I drew on my side lengths. So my bottom here would have to be -1 because I'm going on the negative x-axis. Here would be +1, and hypotenuse is always going to be positive. So now if I wanted to say what sine is, it's not actually sine 45 anymore, because this is actually my angle that I'm calculating. So 45 is my related angle. I know if I go all the way, I'd be at 180, so I just have to back up 45. So I just have to figure out 180 minus 45, and it would be 135 degrees. So now if I wanted to find the sine of 135, I can use my related angle and go opposite over hypotenuse, 1 over root 2. It's still a positive value, which makes sense because the sine curve is still positive in quadrant 2. It's the exact same value as sine 45. That's pretty cool. So this guy, sine 45, is the same as sine 135. Neat. Okay, why don't we extend it into quadrant 3 and see what happens. Alright, here we go. Quadrant 3. Okay, so here's my initial arm. Next, quadrant 3. And now my principal angle is this giant guy right here. So if I create my right angle triangle, and I make up a related angle, so let's just use 45 again, since that's the one we were using before. This side would still be -1. This side would also be -1. And this would be root 2. The hypotenuse is always positive. So now if I wanted to know what my principal angle is, theta, it would be 180 plus 45, which would be 225 degrees. So now if I wanted to calculate the sine of 225 degrees, I do opposite over hypotenuse, negative 1 over root 2. So now the sine is negative, which makes sense because down here in quadrant 3, sine is negative y values. So there you go. And you can guess it's going to be exactly the same in quadrant 4. So it's pretty neat. We can use the sine curve, we can kind of stick it on a grid and help us use our special triangles to kind of use knowledge of SOHCAHTOA to determine big angles like sine of 225, which we couldn't have done before because drawing a triangle that looks like that would be crazy. So we're able to use this to find whatever angles we want. So let's try one. So let's say I wanted you to find the exact values of, let's do cos 150 degrees. So we'll draw our grid. 150 degrees would be in quadrant 2. So that'll be 50 degrees. We'll connect our terminal arm to the x-axis. And since that's 180, the related angle must be the 30-degree triangle. So we got a 30, 60, 90 triangle. So now I just label my sides according to my special triangle. So I know this would be negative root 3, this would be positive, this would be 2. So I'm just getting that from my special triangles. And if I wanted to find cos of 150, I know cos, I'm going to use this angle, is adjacent over hypotenuse, so it would be negative root 3 over 2. And that makes sense because if I look to my cosine curve, it starts here and it goes like this, forever and ever. So if I kind of hack that into quadrants, okay, I drew that kind of bad, but it would be like this. Yeah, 1, 2, 3, and 4. So as you can see in quadrant 2, cosine is going to be negative, and in quadrant 3 as well. Cosine's just positive in quadrant 1 and 4. Neat. So I'm able to find the exact value. So let's say I wanted to find the exact value of tan 315. Okay, so I'll draw my grid. 315 is going to be in quadrant 4. So that's 315 degrees. So my related angle must be 45. And if I draw my side lengths, I know this is 1, this would be negative 1, and this would be root 2. So now I know that tan of 315 is actually equal to opposite over adjacent. So negative 1 over 1, which is just negative 1. So there you go. I'm able to find values of any trig ratio. And I can even find exact values of the reciprocal trig ratios. So if I wanted to find the secant of, say, 240. So I'll sketch out my triangle. It's going to be in quadrant 3. I know the whole thing is going to be 240. Since that's 180, if I go 240 minus 180, I'll get 60. So I got my 30, 60, 90 triangle. This is going to be negative root 3, negative 1, positive 2. Now I also know that secant is equal to 1 over cos. And since cosine, is equal to adjacent over hypotenuse, I can conclude that secant is actually equal to the hypotenuse over the adjacent. So if I wanted to find the secant of 240, it would be the hypotenuse of 2 divided by the adjacent side, which is negative 1. So it would be negative 2. Okay, so then what comes out of this is there's this thing called the CAST rule, C-A-S-T, and it just tells you which ratios will be positive. So all of them are positive here. Cosine is positive here. Sine is positive here. And tangent will be positive in this quadrant, which is what we observed, right? So if we looked, tan was negative in quadrant 4. Cosine was negative in quadrant 2, which is true. So now when you look at a question, you could do it really fast. You could say like, tan of 120. Okay, so right away you could look and be like, well, I know it's in this quadrant. And you could even do it by knowing, well, the tan of 120, I know my related angle is going to be 180 minus 120. So I know my related angle is 60 degrees. So you could just jump right to like, oh, I know my special triangle for 60, 30 is going to be root 3, 1. I know the value is going to be negative because it's in the sine quadrant. And tan is opposite over adjacent, so it's going to be root 3 over 1. So you like almost don't even need to sketch it. You know if it's negative or positive based on the cast rule. And you just need to use your related angle to find the sides of the special triangle that lines up. Okay, there's also another thing where we stuck some points on a grid. So say we had the point, I'm just going to use easy numbers, I'm sorry, like 3, negative 4. So let's say we graphed that. So positive 3, negative 4. So here it is. A terminal arm. There's our initial arm. So here's our angle. So the question might say, determine the reciprocal trig ratios of the angle that's formed. And our angles are always in standard position, meaning the initial arm's here, the terminal arm's in one of the quadrants, and we always connect it to the x-axis. So 3 is on the x-axis, negative 4 is the y value. To find the hypotenuse, I can use Pythagorean theorem. So 3 squared plus 4 squared. So then I know 9 plus 16 is 25, and then I square root it. So I know my hypotenuse is 5. So now if I wanted to write out my ratios, I know that sine theta is opposite over hypotenuse. Cos is adjacent over hypotenuse. Tan is opposite over adjacent. Then if I also wanted to figure out what this angle was, I could use any of these ratios to kind of help me find this related angle here. So sometimes I like to use the positive one. I mean, it doesn't matter. So I'm going to do theta. Theta equals inverse cos 3 over 5. I need a calculator for this. So if I do 3 divided by 5, 6, and if I do inverse cos, I get 53 degrees. So that is actually my related angle, 53. So to find the actual principal angle, I'd have to do 360 minus 53. That's actually not theta. I'm going to call that beta. It's like our decoy. So 360 minus 53. So yeah, we can call that theta, which is 307 degrees. So because sine and cos and repeat themselves all the time, for the same angle, they can have side lengths that are the same, like 3 over 5 can give you multiple angles, but your calculator just calculates the first one. So you have to extend your knowledge and know that the first angle might not be the right one. So you have to make sure that it makes sense. Okay, so that's almost, whoosh, we did that and that. Sorry, this video is so long. So the last thing is trig identities. And honestly, I don't have any offhand, but for trig identities, I'll try to make one up. You're basically just using these identities that we already proved. So sine squared plus cos squared equals 1. And tan x equals, sine x over cos x. And of course the reciprocal. So cosecant is 1 over sine. secants 1 over cos, and cotangents 1 over tan. So you're using all to prove things. Okay, so let's say you had, let's just do a crazy hard one. Sine squared x plus cos x plus tan squared x equals 1 over cos squared x. Pretty sure I remember this one. I think I actually stuck it on the grade 12 test, if I did this right. And you're going to do it again next year too. Okay, so you'll notice you have a left side and you have a right side. Write down the equal sign. So you just work with one side at a time. So I'm going to choose the left side because it looks crazier than the right side. So I'm only going to work with my left side. So I have sine squared x plus cos squared x, tan squared x. And I want to make it equal to 1 over cos. Okay. So the first thing I'm noticing is the Pythagorean, sine plus cos equals 1. Well, I have that right here. So maybe I'll just turn that into a 1. I don't know. Plus tan squared x. And you know what? I'm going to get out the tan because there's no tan on the right. I'm going to use this one. And it's totally cool to just actually square each of these things. So I'm going to say that tan is actually sine squared x over squared x. Cool, now I have a cos in the denominator. That's cool. Now I find a really good thing to do is if you have like something plus a fraction, it's good to combine them. So if I just want to make them have common denominators, I think I'll multiply the top and bottom of this by cos squared x. Because I can multiply a fraction top and bottom by whatever I want. Then I have cos squared x over cos squared x, which is actually just 1, plus sine squared x over cos squared x. Okay. Now I'll combine my fractions. So I add the numerators, cos squared x plus sine squared x, and keep the denominator. And check it out. Sine squared plus cos squared. That's my Pythagorean identity. So I know that's just, I'll just keep this actually. Ugh. Okay, whatever. So I can change my top to 1, and then my bottom is cos squared x, and that's what the right side equaled. So I solved it. So basically you're just subbing stuff in, making denominators. You could be factoring something. Who knows what you're going to have to do. It's just a guessing game. And you just use these trig identities and you just try stuff. And quite honestly, yeah, if you're not good at them, it means that you've only done like 3. If you're good at them, it means you've done like 20 because you just keep practicing and you will get better at them. So good luck, guys. I hope this video helped.